Hi, welcome back to this video series on quadratic residues. Today I will show you how to implement Jacobi symbol calculation using results from number theory. First, let me quickly recall some of the terminology that we have been using. One thing that is important is the Legendre symbol, right? The Legendre symbol is usually defined like this. Suppose you have a number A and you would like to compute the Legendre symbol for that number A in mod P. Assume P is an odd prime, right? A can be any integer. So the definition goes like this. It is made of three possibilities. Okay, 0 if A is a multiple of P. That means we write it like A congruence to 0 mod P, right? That's one possibility. And the other possibility is that A is indeed a quadratic residue. That means A can be written as power of 2 in the group Z star P. That means we will say it's 1 if A belongs to a set of quadratic residue, right? In mod P, it's an element in the quadratic residue, and is equal to -1 if our A, input A, is not a quadratic residue. Okay, remember, quadratic residue means you should be able to find a number that multiply 2 times should give you the number A. Okay, so A is a quadratic residue if you can write A as some B square, for example, in mod P. Okay, so that's basically, sometimes I put equal, sometimes I put 3 lines, but essentially the same in this case. Okay, so this when we are able to find a B that satisfies this, then we call A a quadratic residue, B a square root of A. That's basically the terminology for Legendre symbol, right? Legend or E. Okay. Okay. All right. So I will leave it there. And then I'm going to talk about something called Jacobi symbol. Okay. So which is an important concept we need for our crypto system that I'm going to build later. So how do we compute Jacobi symbol? Jacobi symbol is computed on composite numbers as opposed to P. We need a composite number N. Composite means made of one or more, well, at least 2 primes, definitely, right? Not one, but two, at least 2 or more. So we can actually recursively define this. It's nothing but A. If you know the prime factors, it's easy. Let's assume we know the prime factors of N for a moment. Then we do like this. A into Pi, if Pi is one of the factors. Let's assume there are E factors, Ei factors. Okay, then we do it all the I's, right? P1, P2, K. Okay, let me explain what it is in a moment. So there are K factors for N. Okay, maybe something like this. N is made of P1, P2, Pk are the factors of the number N, right? And it's possible that P1 may be repeated E times. Then we write to the power here. Okay, that's basically what it means. So you could say Pi power Ei means P1 repeated E1 times, P2 repeated E2 times, and so on. So essentially, if we want to find the Jacobi symbol for a number A in a composite group N, we can use the prime factors to compute the Jacobi symbol. But oftentimes we do not have prime factors available in front of us. It's not easy to compute the prime factors of a number N. Given large number, especially, it's difficult to do that. So we need some other way to compute the Jacobi symbol without knowing the prime factors. So that's what I'm going to talk about now. So it's very interesting that there is an approach based on a number theory that will help us to compute Jacobi symbol without knowing the prime factor. That approach is based on the law of quadratic reciprocal or quadratic residue. Okay, it's called quadratic reciprocity law. Okay, so I'm going to use that law to compute the Jacobi symbol without knowing the prime factors. So if you search in a number theory book, any decent number theory book, you will be able to find usually quadratic residue discussion, right? And in that book, you very likely that you'll have something like quadratic reciprocity law. Okay, and as a matter of fact, there are multiple extension of that law. One that we need is this very important property. For example, if you're having two numbers m and n, let's assume both of them are odd numbers. Okay, m and n are odd numbers, positive numbers. So this law is telling us that if you want to compute the quadratic residue of m in composite group n, it's enough to do this. It's enough to do compute quadratic residue of n in m. You're basically swapping n and m, provided our m equal to n equal to 3 mod 4. Okay, if you have this relation true, then you could say that instead of computing Jacobi symbol of m in group n, you will be doing n in m. So if this is not true, right? If this property is not true, that m is not equal to m or n is not equal to 3 mod 4, then you will just do n in m without the minus in the front. Okay, so this is one of the most important properties of quadratic residue that we will leverage in terms of computing the Jacobi symbol. And there is one more thing finally that we need to spell out is if the number m is made of, say, some 2 power k times t, right? If we can rewrite the number m as 2 power k times t, and t being an odd number, some odd number, right? Then there is one more property that we will leverage to compute the Jacobi symbol. Okay, how? I'm not proving that, but I will just state the property. I will just state the property that instead of computing m in n Jacobi, right, we will be doing a small trick. We will be computing Jacobi of number 2 in group n, right? Power k, okay, that's the k that you found out here from your m, right? I will show you how to convert the m into 2 power k into t. That's not difficult. And then we convert it, we compute the Jacobi of t in n, and that's basically what we need. This property and this property, these two properties, let me put it in a box. These two properties will help us to compute the Jacobi symbol without knowing the prime factors. As you can see, I am not using anywhere here the factors of n. Okay, that's the beauty. The only check we have to do is we check whether our m and n are both 3 mod 4. If it is true, then we use minus quadratic residue. We compute the Jacobi of n in m instead of m in n. We swap. If this property is violated, we just ignore the minus and we compute quadratic residue of Jacobi of n in m. Okay. If we found out that our m can be written as 2 power k times t, where t is an odd number. Remember this whole thing has to be an even number, right? Because 2 power k is an even number. Assume k is non-zero. Okay. Otherwise, m is the same as t, and the recursion will not terminate. Okay, or it makes no sense because you say m by n is equal to m by n, which is true, but it doesn't solve anything. So you can assume that your k is greater than 0. So in that case, if we can write m as 2 power k times t, we can leverage this interesting formula that connects Jacobi symbol of m in n to Jacobi symbol of 2 in n power k times Jacobi symbol of t in n. So this is the Jacobi symbol that I'm talking about, right? General formula. This is the Jacobi symbol, and this is the Legendre symbol because this is a prime here, and here is a composite. All right, so we have hopefully clarified how these things are related. Now I'll show you a simple Python program, and we'll do a basic analysis very quickly. Okay, let's get it going. So what you're going to see is my Python implementation, and I must warn you that I have not considered deeper analysis in terms of constant time computation, branch-free computation, and so on. So it's not necessarily ready to use in a real project, but it's helping to understand the behavior of Jacobi symbol. Okay, so what I wrote is basically a very simple Python program called Jacobi.py, right? And the program is essentially codifying the properties of the law of reciprocity. And the law of reciprocity I mentioned to you earlier is made of the important properties. This is the property that I was talking about, right? And when you convert it into code, math somehow disappears. But anyway, so here is the property with respect to m and n being 3 mod 4. This is the property related to if we can write m as power of 2. This is the property, and that's basically the rest are all simple corner cases that we have to take care. So with this piece of code, what I wanted to show to you though is that nowhere here I assume that I know the prime factors of n, right? Nowhere here, and nor m, of course. So given the goal of this function is to compute the Jacobi symbol of m in group z star n. Okay, that's basically the goal. And I mentioned to you that if you are given a number m, you can easily find the k and t using this little trick here. That's basically I'm not going to talk about the details, but as simple as this will help you to find the k and d. Okay, k and t. All right, so we have the basic code in place. Now let's play with the Jacobi symbol and see whether we can understand the insights. Okay, I'm going to import into Python, right? From Jacobi import star, and I will do some very basic computation. Like for example, I will take my p to be prime factor of p to be 5, or let's take simple q to be 7, right? So my n will be 21, and actually you don't need to know the prime factors, but I will show you the benefit of knowing it so that you can compare how the Jacobi and Legendre are related in action. So what I'm going to do is very simple. I'll say, what is the Jacobi of say number 1? Let's start with 1 in n. Okay, since 1 can be written as power of 1, we would expect the Jacobi to be 1 can be written as power of 2, right? Because it's easy to check that. So of course we get the answer to be 1. Very, very nice. But let's do something crazy. Let's take a number for which we know for sure it is not a quadratic residue. For that we need to generate a quadratic residue table, right? And now I need to import my quadratic residue code and compute quadratic residue of say the group z star 21. Okay, I have this, and if you remember my previous segments, you have to look at the column 2. So the only numbers that have quadratic residue are 1, 4, and 16. Therefore, if I select anything else, either, well, we have to be careful here. If the Jacobi symbol is -1, we know for sure the number is not a quadratic residue. Okay, so let's try a few things now. So let's compute quadratic residue and check the Jacobi symbol of say number 2 in group 21, z star 21. 2 doesn't occur as part of the second column, right? The only elements are 1, 4, and 16 are part of the second column. That means 2 cannot be a quadratic residue. Okay, so let's see what happens when you compute the Jacobi. It says -1, which is perfect because we know for sure if the Jacobi symbol is -1, that number cannot be a quadratic residue. But let's try more numbers. We will see some interesting patterns now. What about 3? The Jacobi symbol is 0 because, of course, 3 has factors with 21, right? Therefore, Jacobi symbol is 0. That's perfect. What about 4? 4 doesn't have any factors with 21. Let's see what happens with 4. 4 is part of the second column here, right? Here is 4. 4 can be written as 2 power 2. 4 can also be written as 16 power 2 in 21, or 19 power 2 is also 4. So in this case, we expect the Jacobi symbol to be 1. Okay, so here you go. Jacobi symbol is 1. All right, but let's try more. Let's try 5. 5 is also 1, which is very interesting. Why is 5 having the Jacobi symbol of 1? Let's confirm. 5 doesn't occur as part of the second column, right? Second column has only 4, 16, 4, 1, 16, 1, 4. Remember, each element has 4 roots in z star 21, but 5 doesn't occur. But nevertheless, Jacobi symbol is 1 for 5 for a particular reason. We can actually check the quadratic residue of the prime factors of 21, which are 3 and 7. And we can see that 3, neither in 3 nor in 7, 5 is a quadratic residue. Okay, so we'll do now. Let's look at the prime factors of 21, which is basically 3 and 7. And let's look at now quadratic residue of z star 7. We can be sure that 5 is not a quadratic residue in z star 7. That's important. Okay, so we must see now when we look at this, we get a -1. Yeah, you can see here in the second column only numbers 1, 2, 4 are quadratic residue. Therefore 5 is clearly not a quadratic residue. That means the Legendre symbol for 5 is -1. Actually, we can instantiate the Jacobi symbol function like this, which means I expect now the Jacobi of 5 in 7, which is same as Legendre symbol because 7 is a prime. We should get an answer -1, which is perfect, which is -1. Okay. We can do the same with 3 because 3 is also another factor of 21, and I get -1. Perfect. So important lesson is that if the Jacobi symbol, now what is the Jacobi symbol of 5 in 21? It must be a product of the Jacobi symbol of 5 in 7 and in 3, which is -1 and -1 multiplied, you get 1. So if you get a Jacobi symbol 1 in a composite group, you can say nothing. It may or may not be quadratic residue. That is the most important fact that we will leverage during the next segment when we construct a crypto system. We do know for sure that if the Jacobi symbol is -1, that number cannot be a quadratic residue. Okay, that's very, very important. So what we did is extremely simple today. We basically used the law of quadratic reciprocity to compute a Jacobi symbol of a number in a composite group without knowing the prime factors. And we confirmed that if the Jacobi symbol is -1, the number cannot have quadratic residue. But if it has the value 1, it may or may not be a quadratic residue. Okay. If the Jacobi value is 0, then we know that number is one of the prime factors of the composite number. Okay. That's basically what I wanted to share to you. Thank you very much.